student, we will continue next part of our unit 1, that is Riemann integral. Okay, so today's point is lower and upper integral. Okay, in last lecture we have already seen what are lower sum, what are upper sum, okay, over some partition P. Okay, and also we know this inequality. We have already seen that lower sum always greater or equal small m into b minus a, where m is the lowest value of the function over the interval a to b, and this is the length of the interval. So lower sum less equal upper sum, and upper sum less equal this capital M is nothing but the maximum value of the function over the interval a to b, which is the length of the interval. So from this inequality we know that the lower sum and upper sum are bounded below and also bounded above. That is, lower and upper sum are bounded. So we can take their greatest lower bound and least upper bound. So we define a new term, lower integral, which is nothing but taking least upper bound of all lower sum. See the set SL, set of all lower sum for the function here corresponding to partition P. Now if we take different partition, we will get different lower sums. Set up all these lower partition, okay, lower sum we define it as SL. And since lower sums are bounded, this set also bounded, and least upper bound of this set is called lower integral of here on interval AB, and denoted as integration of f of x dx a to b, and we are write a dash at the lower end. Okay, so what is lower integral? Okay, it is nothing but the least upper bound of set of all lower sum for the function f with partition P. Okay, similarly we have defined another term, that is upper integral, which is nothing but the greatest lower bound, which is nothing but greatest lower bound of the set of upper sum. Okay, see this set of all upper sum. If we take different partition, we will get different upper sum, and since each upper sum is bounded, this set is bounded, and greatest lower bound of this set, which set SU means set of all upper sum, and greatest lower bound of this set of upper sum nothing but upper integral of f on AB, and denoted by integration f of x dx a to b and dash at the upper end. Okay, so this is nothing but the lower integral and upper integral. So we will clear idea by taking example. Okay, later on. So this is the lower integral, this is the upper integral. What is lower integral? Nothing but the least upper bound of set of all lower sum. And what is upper integral? It is the greatest lower bound of set of all upper sum. Okay. Now we will see one theorem regarding upper integral and lower integral. Okay. Very simple theorem. Theorem shows that lower integral for any function always less equal to upper integral for that function over the same interval, same closure boundary interval a to b. Okay. Now this is very simple theorem. Again, this we can prove this using the condition of lower sum and upper sum. Okay. So let T1 and P2 are any two partition of the interval I, which is interval from a to b, closure boundary interval a to b. Okay, we know this condition. So what is the condition? Lower sum always less equal upper sum for the same function f or any partition. So this implies lower sum of f corresponding to partition P1 always less equal to upper sum of same function f with partition P2. Okay, this is the important condition. Now, since lower sum always less equal to upper sum, this upper sum is a upper bound for set SL. What is the set SL? Set SL is nothing but the set of all lower sum. See, take any lower sum of the function f corresponding to any partition, always is equal this term. Okay, so this term becomes upper bound for the set of all lower sum. Okay, so we write list upper bound of S is always less equal up this upper sum of F with respect to P2. Why? Because every lower sum always less equal this upper sum. So set of all lower sum always less equal. So every element of the set of all lower sum is also less equal this term. This term becomes upper bound. So each term from the set SL is less equal this. So list upper bound of this set also less equal this. Okay. So we write list upper bound of the set of all lower sum also less equal this term. And what is the value of this list upper bound of SL? Nothing but lower integral. So we write lower integral of F, okay, from A to B always less equal here U T to F. Okay. Why we have written such inequality? See, we know lower sum always less equal upper sum. So set of all lower sum, take any element of the set of all lower sum of F corresponding to any partition also less equal this term. So that set SL has upper bound this element. So list upper bound from this set must be less equal this element. So list upper bound of SL less equal this element, and list upper bound of SL nothing but lower integral which is less equal this. Now see this inequality. Okay, we come to know from this that if upper sum for function F corresponding to partition P2 greater equal this lower integral, but P2 is any arbitrary partition. So any upper sum for the function F corresponding to any partition always less greater equal this lower integral. So this lower integral is nothing but the lower bound for the set of all upper sum, that is SU, that is this lower integral A to B F is lower bound for set of all upper sums, that is SU. Now this is lower bound. So this is lower bound for SU. So greatest lower bound must be greater equal lower bound of the set SU. So lower bound of the set SU is this. So greatest lower bound of the set SU must be greater than this. So this implies lower integral of F must be less equal greatest lower bound of SU. Why? This is lower bound for set SU. So greatest lower bound for set SU must be greater equal any other lower bound. So this is lower bound. So greatest lower bound must be greater equal this element. And what is this? Nothing but upper integral. So this implies lower integral A to B of F less equal, what is this? Upper integral. Upper integral A to B of the function F. Okay. So we have proved that lower integral always get less equal upper integral for any function F corresponding to same interval A to B. Okay. So friends, we have just seen a inequality corresponding to lower integral and upper integral. So we have seen that for any function lower integral is always less equal upper integral. Okay. But when for some function here lower integral and upper integrals are equal, then that function here is said to be Riemann integral. Okay. The function for which lower integral is equal to upper integral, that is both have common value, same value, then function f is said to be Riemann integral function, and denoted by f belongs to R or f belongs to RAB. Here R is not a notation for real numbers. Here R means function is Riemann integrable, and RAB means function is Riemann integrable over the interval A to B, closed and bounded interval A to B. Okay. So whenever function is Riemann integrable, lower integral and upper integral has the same value, and that same value is the integral Riemann integral of that function. Okay, the quantity f dx, okay, which is common value of lower integral and upper integral, is called Riemann integral of function here over the closure bounded interval R. Okay, so this is the definition of Riemann integrable functions. Okay, so for functions to be Riemann integrable, it lower integral and upper integral must be equal. Okay, so now we will see example of Riemann integrable function. Okay, so question is, show that any constant function defined on closed and bounded interval is integrable, that is Riemann integrable. Okay, so you have to prove that any constant function on closed and bounded interval is always integrable or Riemann integrable. Okay, so how to prove some function is Riemann integrable? So to prove function is Riemann integrable, till we know only one condition, that is prove that lower integral is equal to upper integral. Okay, so for finding lower and upper integral, you have to first find lower sum and upper sum, and to find lower sum and upper sum, we have to take some any arbitrary partition. Okay, so function is any constant function. Okay, so we write f of x is equal to some constant number c. This is f of x is equal to c is some constant function. Okay, define on some interval I is equal to closed and bounded interval AB. Okay, so now to find lower sum and upper sum, we will take some arbitrary partition of this interval. So take partition P is equal to, okay, so first point is A. We write it as x0. Second element we take x1, x2 up to xn minus 1, xn. Okay, so we have taken this partition where xn is nothing but the point, last end point B. So this is function, constant function, this is the interval, and we have taken some arbitrary partition of this interval. Now we will calculate lower sum corresponding to this partition and upper sum corresponding to this partition. Okay, so what is lower sum? Lower sum is nothing but the sum of product of small mk into delta xk, where this small mk means minimum value of the function or kth interval, and delta xk is nothing but the length of kth interval, and some values form k is equal to 1 to m or all subintervals. Okay, now see here, function is constant function. Okay, so take any interval, value of function is fixed c. Okay, since this function is constant, put any value of x, f of 1 or f of x0 or f of x1, will get c. Okay, this is constant function like this. The constant function. Take any interval, it has same value. Okay, constant function. So since function is constant, our value of function is fixed in any subinterval, which is c. So here lower sum is equal to summation k is equal to 1 to n small m k delta xk. But here since function has fixed value c, here maximum value, minimum value are same and value is c. So over any subinterval, maximum value is c and minimum value also c. So if it is constant, we can take it outside. So this becomes summation k is equal to, okay, so we have to take mk outside. This is equal mk summation k is equal to 1 to n delta x k. Okay, now sum of delta x k. What is the delta x k? Nothing but the length of kth interval. So sum of all subintervals of the interval. So this is our interval a to b, and these are the subintervals first subinterval, second up to so on. So sum of each subinterval is nothing but the length of the interval. So sum of the all subintervals of the interval nothing but the length of interval. And length of the interval a to b is b minus a. So lower sum becomes mk as it is outside, and this sum is b minus a. Okay. And under mk small mk is what? C. Want some fixed value c. Okay. So c into b minus a. This is the lower sum. Now similarly, is find here upper sum. Okay. So for upper sum, we know the formula. Formula is similar to this. Only difference is here we take maximum value instead of minimum value. So upper sum. So upper sum is equal to summation k is equal to 1 to m capital Mk delta xk. Again, function is same constant function. So capital M value is 6, which is c. We can take it outside. So this become c outside, and summation k is equal to 1 to n length of each subintervals. So length of all subintervals, nothing but length of full intervals. So this become c into b minus a. Okay. Now we have calculated lower sum and upper sum, but we have to find lower integral and upper integral. So what is lower integral? So lower integral of this function nothing but the supremum or least upper bound of the set of all lower sum. See, lower sum is constant c into b minus a, fixed value. Okay. So take any partition, we will get lower sum c into b minus a, fixed value. So this set has a fixed elements c into b minus a. So lower integral is nothing but the supremum of the set of all lower sum. But lower sum, set of all lower sum contain only fixed elements c into b minus a. So lower integral, which is nothing but the supremum or least upper bound of the set SL, that is set of all lower sum. And set of all lower sum has this element c into b minus a. So least upper bound also c into b minus a. So this is the lower integral. Now upper integral. Upper integral is least greatest lower bound of the set of all upper sum. Now each upper sum is fixed with c into b minus a. So set SU, which is set of all upper sum of the function f, is has the fixed elements c into b minus a. So the upper integral, which is nothing but the greatest lower bound of upper sum, set of all upper sum, also fixed, which is also c into b minus a. Because supremum of set which contain fixed values is nothing but that fixed value. So upper integral, greatest lower bound of set of all upper sum. Set of all upper sum set contain fixed value c into b minus a. Supremum of this nothing but c into b minus a. So here lower integral is c into b minus a, upper integral also c into b minus a. So here lower integral is equal to upper integral, which is equal to c into b minus a. This implies this constant function is Riemann integrable, and its integration or Riemann integration is c into b minus a. Okay.